let's look at global winds again. Here's the Earth, and I'd like to have you actually take notes. 0 degrees latitude. So actually try and draw this. 90 degrees north latitude. And this will be good practice for you to draw it yourself. Divide up this quarter here into thirds, and same thing all the way around. And then draw the latitudes. These are 30 degrees latitude and 60 degrees latitude. I've given a little space here so that we can draw some additional things in that space. 30 degrees south and 60 degrees. Now think about the equator. At the equator it's warm and the air is going to rise because warm air is less dense than other air. So we've got rising air at the equator. And then when it gets up at high altitude, it splits and goes both north and south. And this makes a big loop, and it would go all the way up to the North Pole if it weren't for the Coriolis effect. But because the Coriolis effect is happening, the Earth is spinning on its axis, it can only get up to 30 degrees, and then it cools off enough to sink. Now it's cold air sinking. So here at the equator we have rising air. As the air rises, it condenses because it's going higher in the troposphere. So we're going to build some clouds here and some rain. So at the equator it's rainy because the rising air condenses as it cools off in the troposphere, and that allows clouds, and then clouds lead to rain. Now that creates a low pressure, not the rain, but the rising air creates low pressure because as the air rises, the molecules are leaving that area, and with fewer molecules, there's lower pressure. Also, you can think of that warm air as being less dense, and being less dense, it's not as heavy as air other places, and that creates a lower pressure. There's less air pressing down, less mass pressing down on the area, so lower pressure. As the air sinks at 30 degrees, instead of causing condensation, it's going to cause evaporation. So you're going to get sunny skies at 30 degrees. So here's our sunny skies. That's supposed to be the sun. So it's sunny, sinking air, high pressure. By now, I hope that you figured out that high pressure is associated with sunshine and the lack of rain, and that low pressure is associated with rain. So this is high pressure because it's dense, cold air sinking. It does warm up as it sinks, but it's denser than the warm air, and so it's higher pressure. Or you can think of more molecules coming down to the Earth's surface and creating higher pressure there. Now what happens at the poles? In polar regions we have sinking air because it's cold there. Now as that air sinks, it's actually warming up. It starts off super cold and then it gets just down to cold. So it's warming up, and warming air causes evaporation. So this is also going to be an area of clear skies, lack of snow. Okay, so now this air is going to split and then rise at 60 degrees. Now these big loops are called cells, and the one between the equator and 30 degrees is the Hadley cell. And this is also a Hadley cell. And the one up here at between 90 degrees and 60 degrees is the polar cell. Let's draw another one over here. Polar cell, polar cell. Now what happens in between we have 30 degrees and 60 degrees. We have the sinking air at 30 degrees. Some of that air goes towards the equator, but some of it heads north and makes a big loop there, one of those cells. And this cell is called the Ferrel cell. Ferrel cells have warmer air because it's coming from the subtropics here, heading towards the North Pole here, or in the southern hemisphere, coming from the subtropics, sinking air, and then rising. So think about the air at the poles. The polar air is going to be very cold, and that air, when it comes and meets up with the air in the Ferrel cell, it's going to cause the Ferrel cell air, which is warmer, to rise over it. Where the Ferrel cell and the polar cell meet is the polar front, and that's where the extratropical cyclones we've been talking about occur. Looking at this whole diagram, now those are the cells around the outside, but what's happening to the wind on the surface? Look at this Hadley cell here. We've got wind blowing from the high pressure towards the low pressure. That's normal for wind to go from high to low. Fluids are moving from high pressure to low pressure. Here we have the air, then it's going to go towards the low pressure, but in the northern hemisphere, it's turning to the right because of Coriolis effect. Now, I would like you to draw your arrows as straight arrows. Don't draw them curved. The reason I ask you not to draw them curved is because a lot of times students will draw them curved and then they curve them a little too much and they go the wrong direction. So we've got air that would have been coming straight from the high pressure to the low, but with the Coriolis effect, it turns to the right. That's a right-hand turn. Same thing in the southern hemisphere, except that now it's going to turn to the left. So going from high pressure to low pressure, the wind is going to head this way. Okay, notice that's wind in the Hadley cells going from the high pressure to the low pressure. We also have high pressures and low pressures other places. See if you can figure out where another high pressure is. Here's another high pressure right here. I'll just call it HP. High pressure. And then we have another low pressure where the air is rising at 60 degrees. Now also, if you think about that air rising at 60 degrees, if it's rising, is it going to condense or is it going to cause evaporation? It's going to cause condensation because the air is rising and cooling. So we're going to have some more clouds here, and here's some rain, and let's put in some snow. It's getting a little messy in here. Rain and snow. Rain here and snow. Okay, we need some more winds. Let's get some winds going between this high pressure and this low pressure. From high to low, turning to the right. Right-hand turn. Again, draw your arrows straight rather than curved, just to make sure that you don't end up taking them off in the wrong direction. And then from the pole, high pressure towards low pressure. Another right turn. The right turn coming towards you, so it's that direction. From here at the South Pole, heading towards the low pressure, turning to the left in the southern hemisphere. And that gives you the wind. Now I want you to notice that all the winds in the northern hemisphere are all lined up in line. They switch directions, but they're all lined up. And similarly, in the southern hemisphere, they're also all lined up. Now, what are these winds called? Each wind has a different name. Actually, I'm going to scoot this over a little bit. And let's name these winds. These are the northeast trade winds. That's these coming from the northeast. These are the southeast trade winds. These are the westerly winds in both hemispheres. And these, between the pole and 60 degrees, are the polar easterlies. Okay, it's getting pretty messy. Now let's just add some more mess. Think about the rain at the equator. If you have land there, what will grow because of all that rain? You're going to have forests in here. You're going to have forests. In fact, tropical rainforest. Over here, you're going to have desert. There's some more desert. You're also going to get desert at the poles. The reason it's desert at the poles is because you have sinking air there. It's dry. It causes evaporation. So I know Antarctica is just covered with ice, but that ice, just a little bit of snowfall, it stays around year after year after year. What about this area of rain and snow? There's an ocean down here, so we don't have a biome at that location, a large regional ecosystem, because it's the ocean. But here you're going to have a forest, and that's called the boreal forest. Oh, this is really getting messy. Boreal means north or northern. You may have heard of the Corona Borealis. It's a constellation, and it's also called the Northern Crown. Now I want you to notice the symmetry of this pattern of global winds. If I put a mirror here, let's see if I can get this lined up properly. If I put a mirror right in here, you can kind of see that at the equator is the mirror image south of the equator compared to north of the equator. See that? Get that back lined up again. Right there.